All right. I think we are live. I'm just joining a little bit early. Just give a chance for people to wander in, do what they do. Let me take a sip of coffee here. Looks like we got pretty good stream health. How's my mic? Levels are good. So I say we are good. So we'll just wait around for a few people. If you're hanging out or whatever, go ahead and drop a nice little hello or something in the chat. That'd be nice to know. Or say hello, things like that. Yeah. So we'll wait just a wee bit longer. All right. So it looks like we've got a few people watching. Hello, everyone. So I guess I'll get started. So I want to finish off. We're getting to the end of talking about predicates and things like that. No, it's Tuesday. I wonder what's going on. Let's see. Oh, looks pretty good. Okay. Hey, Sweetball, how you doing? Oh, yeah. Oh, I did change my day. Julio, that's right. It used to be Saturdays, but then I moved it. Yeah, I moved it to Tuesday. It used to be Tuesday night, and then moved it down to Tuesday morning to kind of help with the European folks. By the time I was live streaming, a lot of them were either in bed or really just didn't want to watch it, so we moved it. Hey, Bob, how are you doing? Oh, it's good to see all of you again. All right, so we're going to finish off. Howdy, mate. We're going to finish off our discussion about predicates and things like that to kind of show kind of an interesting combinator. You don't use it a lot, but you can use it. Oh, thanks, Julio. But you can use it, as we'll see. It's kind of a weak condition implication. Or I don't want to say weak. Yeah, okay, we'll say weak. So it's kind of a weak condition. And it's very rare that we use it in programming. We use it every now and then, but it does come in handy later on, as we'll see, in a few instances. A lot of times. Oh, great. What are you using? I'm sorry, Julio was saying using Crocs at last. Julio, what are you using Crocs with? So with the implication, we're just going to go over, talk about it a little bit. We'll talk about the truth tables, kind of see why it's a weak condition, talk about a few implications, and then we'll jump straight into the code. Now, I was trying to get a camera and all that set up. I was watching Komet's live streams, and I really like what he was doing with, he has like a camera with a notebook. And I just liked how he was doing that. So I went to go get a camera set up, do things like that. And it didn't work out quite the way that I wanted it to work out. And it was ridiculous. I'm sitting there trying to get this camera to work when I haven't even like written out the examples or anything like that. So, oh, heck yeah. Oh, an Express REST API. Hey, Julio, check out Paperplane. There's a cool library that we use at work called Paperplane it acts as a web server, but it's a functional web server. Lets you do things with functional composition instead of the normal middleware pattern. It's actually pretty cool. I'm not saying, hey, make this your project, but if you're into building REST servers, you should check out Paperplane. It's pretty great. All right, so without further ado, oh yeah, the other thing with the camera. So what we're gonna do is the stuff I wanted to show with the camera, I'm just going to put up on this little board, right? And then take it from there. So, okay. All right. So I guess let's get started. And I guess the best way to get started is with anything logical, we'll talk about the truth tables, okay? So we'll have two predicates. We'll have a P. Oops. We'll have a P. Oh my goodness, it's called typing. See, you did it again. And we'll have a Q, and then we'll have P implies Q. Okay, so for this, if we have true, true, with implication, we're going to get back true. And I'm just going to write this in, then we'll explain like why it is this way and kind of how it works. So we'll do true and then false. And that's going to come back as false. And if we have false, true, this comes back as true. And if we have false, false, this comes back as true as well. So I know this looks a little weird, but one thing to say is the reason why it's such a weak condition is there's really only one thing that will let this contradict or be a failure or report false. And that's going to be when the predicate P is true, but the predicate Q is false. And the reason why that is how implication works. It says if this is true, if P is true, then this. It's basically an if-then, right? So if P is true, then Q. So if P is false, it's still true, right? Because it's still, you didn't have to evaluate Q. Q depends on P. So that's kind of the basics of implication. So it's really weak in a lot of cases because the value of the first one is pretty much ignored unless it's true, and then the second expression is evaluated. So we'll see a couple examples in code, like what makes this really weak. So a couple, how would you say, English or like speaking examples of this would be, what is that one? So it is raining. If it is raining, then the roads are wet, right? So we'll have is raining, and then we'll do wet roads. So you see how the second thing is dependent on this first thing, right? Well, and I don't want to say it's independent of it. For instance, if we have these wet roads, there might be other reasons why the roads are wet, not just because it's raining. But if it's raining, then the roads are wet, right? So say we were able to pass something in here, we would evaluate this. If this is true, then the roads are wet. If it's not raining, then this is still true, because we never even evaluate whether the roads are wet. The roads could be wet, but we didn't evaluate it, right? Does that make sense? Another more mathy thing is we could say if X or something is greater than, oh, goodness gracious, is greater than 10, then that implies that that same thing is greater than 5, right? So if this is true, this is also true. See, the thing that would make this false, or could make it false, is this, right? Going the other way. Because it doesn't really imply that. Anything lower than 10 would imply it. But this still could be true. Like say I put in a number like 30, right? So 30 would evaluate this to true. But it's not going to evaluate to true if it's, say, 11. Right? But this would be true if it was 11. So that's kind of how the implication works, right? Yep. So again, there's not really too much to talk about here. What we can do real quick before we get into another example is kind of give you an implementation. So let's look at an implementation of this. We're going to need a couple things from Crocs, because remember, this is pretty much an if-else-then, or an if-then statement. So we could bring in if-else, and we'll bring that in from Crocs. So we'll do require Crocs, bring that in. And what else will we need? We're going to want to make sure, well, we'll just do this. So we'll do implies is equal to if else. And with this if else, we'll say the first parameter to if else needs to be some sort of predicate to evaluate a value with. So we need two predicates to come in here. So we need a P and a Q. So let's go ahead and set this up with a P and a Q. And now we have two predicate functions to come in. Down here, we can now say, if the first thing P is true, then go ahead and evaluate Q and return the result. But if it's not constant, we want to return true. We don't even want to evaluate constant. We do not even want to evaluate the second thing because remember, if this is false, which would put it into this falsy condition, is that like when from Ramda? Kind of, except we need this to actually change what the value was. So if you could think of it as when, but whenever that thing is false, instead of providing identity back, we would provide back true as a Boolean. Oh, and I'm sorry, I should probably give a SIGI for this. So we take two predicates that go from an A to a Boolean, and we'll take another predicate that goes from an A to a Boolean, and we're pretty much bringing back or making this, once these are partially applied, that'll then get us back another predicate, A to Boolean, right? So again, just like with all the other combinators and things along those lines, like and or, after you apply the functions that you want as part of your, how would you say, expression? That's not really an expression. After you apply your functions to it, you get back another A to Boolean that could work with anything else, right? So it's still, this works just like and when and like all of the other ones. All right, so we have this implies. Now, one thing though is this if else is going to take care of coercion for us, right? So it will check this. If, say, we bring back something that isn't a Boolean here and we didn't match it, this is going to take care of it and make sure that it gets evaluated to a Boolean. But we want to keep this signature straight. Like, we want to make sure this is a Boolean. So if for some reason, if the Q provided is not a Boolean or does not return a Boolean, then what we want to do is just make sure that it gets coerced as such. Boolean. So what we're going to do is just throw that in there for coercion. And I guess I can give an example of what that would look like. Compose without the composition of throwing the Boolean in there. So since we cannot guarantee, we don't have type checking, static type checking, things like that, we want to make sure that we're being very truthful with our signature. So we're just going to coerce whatever the result of Q is into a Boolean. Does that make sense? I'm going to take a sip of coffee real quick. Looks like we have pretty good stream health. Looks like I'm lagging a little bit. Alrighty. Okay. All right. So that's this is basically how you would implement implication. So before we get into other examples, I want to show kind of a mathy example. Well, actually, let's see why this is weak first, and then I'll show you an instance of why this is strong, but we'll do it more in kind of a mathy way, right? So let's take something, we'll make a nice little function here, and we're going to call this has length, right? And we want this to be a Boolean, or a predicate, I'm so sorry. So we have our has length, and then this is going to go from any A to a Boolean. We're going to go ahead and bring in length from Ramda, and require, what is it, Ramda. All right, Ramda. Oh, that's making little squeaky sounds. Let me. Okay. So now to here, all we really need to do is set length. But what we're going to do is, because we've already said it's a Boolean, we're going to do the same sort of thing here. We're going to take some A. run it through length, and then when that comes back, we're going to return a Boolean of that, right? So of course, if length is 0, then that's going to come back as false. If length is true, then that's going to come back as whatevs. So what do I mean by weak and strong? Sorry, real quick, Bob asked a question. What do I mean by weak and strong? So if you think about, like, say, an and, that's a pretty strong condition there. Both things need to be true for it to be true, right? It's got a lot of power behind it. So you can say this and that very, very, how would you say? With a lot of gusto. No, I shouldn't say gusto. It's very easy to provide that constraint or that condition, and you don't have to make a lot of special cases to account for other things. So it's a very strong condition. Let's get through this, and then I can kind of show you why this is strong versus why this is weak. I probably shouldn't have been using that terminology yet, but yeah. So how has length is going to work? I'll get back to that, Bob, I promise, for sure. So how has length is going to work is if I bring this in, that's going to come back as false. And if I do 1, 2, 3, that's going to come back as true. Notice if I didn't have this compose here, if this was just length, I didn't have to do that. If this was just length, notice that would give back the number 3. And we didn't say that this is going to bring back a number. We wanted to say that this brought back a Boolean. But if we do the has, so that's why we do that coercion right here with composing that in. Right? But this also works not just for strings, or not just for arrays, but it's also going to work with strings. Right? So this will come back as false. And we'll say, hello, this comes back as true because there's length to it, right? If that makes sense. Oh, message redacted. I'm sorry. Okay. All right, so now we have this has length. We have all of that. Now, let's use implies, and we'll use this to say const when array has length. So we're saying that when this is an array, make sure that it has length. So we'll use implies by going implies. And all we do is bring in isArray from Crocs as our P. And that should go at the end here, isArray. And jump back down. And we'll do has length. Okay? So now, if we'll do this, when array has length, and when we pass this in, we'll notice that we have our contradiction, right? So this is false. The first one passed, yes, this is an array, but the second one failed because it didn't have any length. But if we put in 1, 2, 3, 4, notice that's true. So the first condition is true, it is an array, and then the second condition is true, it does have length. So this is true. Now, let me show you why this is pretty weak of a thing. Oh, and I'm sorry, this should be when has length. This, again, is a predicate, so it goes from A to Boolean. The reason why this is bad news bears, or not bad news bears, but not just something we would see in code a lot, is because look what happens when I put an empty string in. See, that comes back as true. So it's only going to evaluate whether something has length if the first condition is true, being isArray. So you can think of kind of like switch case or a when, right? So just like, who was it that said that? It was Bob. So just like Bob, it kind of acts as a when, right? Like some sort of switch case. When in its array, go ahead and evaluate this. But if it's not an array, don't really worry about it. We're going to move on. And that, Bob, is why it's like a when and why it kind of feels pretty familiar. So it is a when, but in the, like you were saying, except in more of a predicate sense. So that's awesome. Good show. Good show, mate. All right. So we don't run into this a lot because really we would want something like an and or something here. So that way, if it wasn't an array, right? So we could do something like, let's just bring in and, right? So we'll bring in our and we'll do is array and has length. See, this is what we're typically working with. These are the types of things that we really care about with doing, you know, your normal top-down imperative function or imperative programming, you know. But if I put a string in here, of course, that's going to come back as false because it passes the is array, undefined or null, one of the types. Of course, that's going to be false because it's not an array, you know. So these are the types of things we're used to working with. Where implies and being such a weak condition or something that it's really hard to fail, man, I should probably stop saying weak because I don't have a good definition for that. It just feels weak to me, you know, is when it comes down to when we're talking generically about systems, and a lot of times this comes into play with what's called a universal constructions, universal properties. When we're defining these things, we can use this weakness because we don't really care about whether something, in most cases, we don't care about this being equal to this. We care about things being equivalent to each other, right? So this weak condition lets us evaluate everything and really only apply certain rules or properties or talk about certain rules or properties that we care about for a given concept that we're speaking about, right? So for instance, think of the definition of an injective function, right? So an injective function, we'll say we have an A, B, and C, right? A, B, and C. Let's make this just a wee bit smaller. So we'll have a set X and we'll have a set Y. Why? Because we love you. And maybe this is A, B, C, and this is 1, 2, 3, 4, right? So we have, and I need to move over here just so I can get the real time on this. So see how we have this 1, 2, 3, right? Just like that. So this is a set of ABC, 1, 2, 3, 4. An injective function is one that for every single B, and we'll bring this to 2, for every single bit on your input or your source, it points to a unique value in the target. Notice it doesn't need to be like a set of 3 to a set of 3. We just need to make sure that every single one of these inputs points to one and only one, or well, I'm sorry, not one and only one, but for every single one of these, this one right here, how would you say? So 2 of these can't point to the same one, right? That would be a good way of saying that. I'm trying to avoid the implication talk so you can see what how implication could be used here. So how you could represent that is you could say for all x1 and x2 belonging to x, if f of a is equal to f of b, then that implies that f of x1 is equal to f of x2, then that implies that x1 is equal to x2. Right? So let's see. So what we're saying here, and is this backwards? I hope this isn't backwards. So what we're saying here, hold on, let me see if this is backwards. No, it's not. Okay. So what we're saying here is, there we go. So for all x1 and x2 belonging to x, if I were to take any a and then apply it to some function f, so we'll call this function f, if I were to apply it to any one of those, and if it's equal to f of x of 2, then x of 1 is equal to x of 2. So how you would do that is you would say, all right, I have an a and I have a b. f of a goes to 1. F of b goes to 4. So they're not equal. So I don't even evaluate that. So far we're still true. This is an injective function. If I were to do f of c, or f of a is 1, f of c is 2, again, this does not pass, so we're still a injective function. Then if I do a as my x1 is equal to 1, and I do a of x2, which is equal to 1, then I know that 1 equals 1, so a must equal a, right? So a contraexample of this, or not a contraexample, I'm sorry, but a false example of this to a function that is not a injective function, we would take, let's do that, and we'll bring both of these to 4, right? So now we basically have a goes to 1 and b goes to 4 and c goes to 4. So if we look and evaluate, let's see if we do a goes to 1 and b goes to 4. So that is not equal to that. So we still, at this point, still have a injective function. But then when we look at b and c, b goes to 4, so this evaluates to 4, and c goes to 4. But b is not equal to that, so this is false, and that says that this is not an injective function. So conditions like that, and next time I will make sure, next session that I do the drawing in, I will make sure that I actually have a camera, because that was just ridiculous what I just did right there. But hey, what can you say? So that's where like the weakness of implication comes into play very well. Like in programming, we we use our nots and we use our ors a heck of a lot more because it just works out a little better that way, right? So yeah. That is a little bit about implication for now. I want to talk about one more topic because otherwise if I don't, it's going to get confusing before we go and show more examples of implication and like when you can use it and, you know, well, an example of when you would use it in normal programming. So for the first one, the next thing I want to talk about before we get on to that is actually unions of types. Now, you're going to have a little imagination with me. Welcome to my imagination. So one of the curses / benefits, or no, let's say one of the strengths / weaknesses of JavaScript is the fact that we're a dynamically typed language, right? We are dynamically typed. So what that means is I can make a function work with any type in JavaScript, any type at all, whether it be a string, whether it be, you know, an array, whatever the thing is that we're working with, there's nothing that would stop a function from being applied with a type that we wouldn't be expecting, right? So this could lead to a lot of, if you're not writing specs or if you're not used to working in a dynamic language, so you don't use things like reasonable defaults or certain patterns that a person that's been doing, dynamically typed languages would do to kind of avoid that mess, then a lot of times you could run into a lot of regressions and things like that. So that's one of the drawbacks to it. And on a really complex large app, if you're not careful and you don't take steps, it could get away from you real quick. And you could end up introducing a lot of regressions and things like that. So that's kind of a bummer part of it. The strength of it is you can move really fast without definitions, without having to create a whole slew of functions. I can write one function that deals with multiple types and just be on about my merry way as long as that's communicated. I have reasonable defaults, things like that. The other thing is it allows us to create ad hoc type unions, right? So what do I mean by a type union? So say we have two sets. Say we have an A, and we'll define A as, we'll have elements X, Y, and Z. And then say we have a B, which is another set that's defined as A and B. See, just like, let me move my screen again so I can get the real time. So just like that, right? So B is defined, that's with that little dot thing. It's more like an assignment. A here, we're going to call a 3 or a triple set called XYZ. And then we have just this binary Boolean-ish type set A and B there, right? So with JavaScript, when we have different things like that, for now, with that diagram, we will think of A as maybe a string or undefined, I guess, right? Now, when I say string, I'm meaning, we'll do function. I'm meaning that the value could be any string that anybody could ever imagine and actually hold depending on your computer's resources in memory and process with JavaScript. Every string imaginable is available to us, right? And then when I say unit, so we're going to say this takes either a unit or a string. So we'll just call this sumfunc. Sumfunc. Okay, and then it's going to take some value x. And then we could do some things. So one of the ways we can check to see if it is a undefined is we'll do if, and we'll do is same type. So in Crocs, this is a really powerful is same type function here. It lets you either put in constructors or instances, and it will check the types against the two to see if they're the same. So we'll just do undefined, and then we'll do x. So this is doing something with equals, but we're checking really to see if the instance of undefined is equal to this other instance. But we don't really we're talking about types here. We're not really talking about values. So it makes sense to me to actually use the is same type in this type of situation. And if it is, let's go ahead and just return a string, right? So we'll have this sumfunc that takes a, let's call it string plus unit. And in JavaScript, we have available to us up to 3 unit types. We have nan, null, and undefined. You can consider them unit types. Nan gets a little weird because if it's an association to number and things like that. But if anything, we have 2. We have null and undefined, which are pretty much the same thing at a high level. But we go ahead in Crocs and choose undefined as the unit type for Crocs. Because if you think about it, if you don't return anything or the key doesn't exist or things like that, that's actually a unit. Like it'll return undefined. So in those cases, in most parts, there are a few places where null is returned, but a majority of the language, it will just return undefined as a default, right? So we tend to keep that. In Crocs, we use undefined as the unit type. And we represent unit type as this empty tuple, right? And you can think about it like, say I have a function that doesn't take any parameters. Anyway, we don't want to get into that. That's totally derailing it. So here what we want to do is return another string. And then we'll do another check here, is string. And you might see code like this in a few places, right? In some of your apps that you may have. But instead of returning the string, we want to return got string. Or not the question, we want to exclaim that, right? But again, this is imperative, so we need something to do to deal with this. So we will throw new type error, and here we'll say some func expected. Let's see, expected string plus unit. And here we'll just write it this way. All right. So in this case, we actually, it's not that we're taking two types, right? Because we only have one value. We only have one thing that's coming in. We want it to be a string or a unit. That's what we want. But really, we're not getting a string or a unit as our type. It's one type. It's string plus unit. And it's going to give us an instance of that, right? So let's see how this works. If we do something called some func, and we'll pass in, let's pass in null, heck. So we pass in null, and the other thing, we have all kinds of issues here. GG, and let's do is string. That's cute. All right, so we'll do our is string right there. That should take care of that. Good. Some func got null, and we need this to be x. Goodness gracious. I just learned how to program. Nice to meet you guys. So there we go. Now we notice that we get our error back. Some func expected a string plus unit. So we get our error back with null. But right here, if we put in an array, we still get the same thing back. But if we call it with undefined, or, you know, this is what I mean about the unit, or undefined, actually pass it in, then we get our blank string. But if we do like happy from fairy tale, so that's that cute little cat from fairy tale, you notice that we got our got string. So what we really have here, and you'll see this a lot in JavaScript, sometimes with undefined or things like that, we actually have this string plus another type. So it's kind of like a union of the two, right? So going back to our wonderful little drawing that we have our A and we have our B, and they inject, well, let's not get into injections and things. We'll wait till we get to unit types. So they actually can be combined into a type of A plus B. And the A plus B is defined as a set that has X, Y, Z, and A, B inside of it. Also, if we take the cardinal of A and add that to B, we get back the result of that, which is 5. Right? So, looking at this, we now have our A and we have our B, and then those go into an A plus B. And notice how instead of now having a value of A and a value of B, we actually get to pull from the set of A plus B. And if we were to look at the cardinality of these, or how many items are actually inside of there, we actually have 5 items in this one. The cardinality of A is 3. The cardinality of B is 2. 2 plus 3 is 5. So this is where this sum comes in, because it's basically adding together the two different types, right? So in our case, we have every single string that you can imagine in the whole wide world that can be represented in JavaScript or at a program at a given time. Plus, we also bring in an undefined, right? So does that make sense? I kind of went over that, and I know the diagram's probably a little distracting and things like that. But what I'm trying to get is an intuition, or trying to help build an intuition around thinking of the arguments that come in as that argument is part of a type, right? So are there any questions, anything that needs clarification around that? The room is all of a sudden gotten pretty quiet. So I'm going to take a sip of coffee and wait to see if there's any questions or anything. Oh boy, the lag is real, my friends. All right, I'm going to take another sip of coffee, wait just a wee bit longer. All right, Bob's good. All right, I'm going to move on. Okay, so anyway, we run into this a lot. It's one of the benefits. Some people don't see it as a benefit. How do you simulate sum types on the fly? We haven't really got into sum types. We haven't really got into them too much. We'll start talking about sum types once we get into the algebraic data types. But yeah. This is more helping to build the understanding of one argument or one value comes from one place, not really two places when we use them, which will come in handy a little later once we start getting into algebraic data types. Now, I can't really think of a way on the fly to build an actual sum type, but I'll think about that for a little bit. Maybe there's a way we can represent that without having to go to, like, say, an algebraic data type. But that's an interesting question. All right, so let's get rid of some of this stuff. There's a lot of cruft on our screen, so we will get rid of some of it. And I'm going to go ahead and erase this stuff here. Don't really need that. We'll keep the log there. So let's look, and we can make this. We'll come back to that. Okay, so I want to show an example of how we would represent something with disjunction. Still not clear for me how to get a sum type. Yeah, the sum types will come. So this is more of a union of sets, if you would think about it. So instead of us just, being an actual sum type, we're actually, this is more down at the function set function and set level, right? So think of it as, instead of that plus, I probably shouldn't have used the plus, but think of it more as the union, right? So A union B is equal to A plus B in this case, right? I'm just using the A plus B notation just so it makes it easier to bridge into when we start talking about sum types. Basically, that bit that we just made there could be considered a maybe type. But, well, a loose representation of a maybe type through a function. But yeah, we'll get back. We'll get into the sum types. Hopefully, this next section will make it clear as to when we would run into this just programming at the JavaScript function level, right? With types and functions, and types and type functions. So let's create a couple predicates here. We'll create one called isLarge, and what we're going to do with this is we'll bring in prop satis. I always misspell this. Satisfies. I think that's right. We'll bring that in from Lambda. Prop satisfies. Okay. And what we want to check here is we want to see if the length of something is greater than 30. So as we all know, if we were to use the A, B, C, D, E, F, all right. So we'll bring in greater than. We know that greater than, we don't need this anymore. We know that greater than is not point free. So we're going to have to bring in our flip function here. So we'll bring in flip, and here we'll do prop satisfies flip, and we'll flip greater than with, I don't know, let's give it a value like 30. And the prop that we want to verify this with is going to be length. So this can tell us if something is large, right? So we can do, oh, I'm sorry. This is now going to be a predicate, which goes to Boolean. And if we jump down here, we can do is large. And if we put in a string, of course, that's false. If we do 1 comma, and let's do this with a y and then 30p, that comes back as true, right? Let's go back to home and delete to this. Same thing with if we had a string, it would come back true as long as the length is over 30, right? Does that make sense? I got the representation as a union, but the pattern matching spark does not ring for me. Right, yeah. Yeah, it doesn't have the pattern matching. Oh, it looks like Pfizer already has that. Pfizer. All right, so if we jump into there, like with this is large, we can now have a function that can check to see whether something of a given length. Oh, and check this out. Undefined, this won't error anything. Oh, it does error. Sorry. Because we are using Lambda. I should have used, and that's because I don't have the, so this is going to error too. But that's a real bummer. But that's what happens in some cases. But if I were to put in, like, say, a valid object like that, or, 1, 2, or A1, whatever, those all come back as false because they don't have a length. Of course, the null and the undefined are going to error. We could fix that now, but this is not the point of that, right? How that can become a union type or a sum type on the fly. It's more ad hoc. It's not that it's a union type. It's the fact that we can account for the union type in all of our functions is what I was trying to get across by that. Sorry about that. Okay, so now we could represent, say we were to bring in a type of string plus array, right? We could write a function, and maybe we want an array that has a certain length. So we can say a array with length, right? Length. And here all we'll do is do and is array. Okay, and like I said, this is the way we would typically do it, and has length. This is the way we would typically do this with array with length. In normal programming, we wouldn't really use the implies or anything like that. We typically do something like this, right? Okay, so now, say we also, since we're going to be taking in a string of some kind, we want to check to see if it's a large string. So we'll use this is large. So we'll do large string. Okay, and large string is going to be and is string and is large. Okay, so here we have large string, and that of course is an A to a Boolean. Yeah, it's not a union type. Oh, I'm sorry. You got that. You got that. All right. So now if I could check to see large string, right? We'll just, I mean, I think y'all get what's going on here, but just, right? So that'll come back false. But if I do for and then do y with a, oops, we'll do y with a 30p. With a 30p. That comes back true, right? And then the same with array with length. We can, if we put this in, that comes back false. But if it has any length, we get that back just like that. So that would be true. Now, say we have a function that requires both of these. So say we have a function that requires both of these. Now, so we'll have, I don't know. We want something that's going to take either a large string or an array that has some sort of length to it. Who knows what this function is? Maybe it's something to do with, I have no idea what this function is. I'm just kind of riffing here. So say we need to check at the head of our condition to see if all of this is true. Now, one way to do it is with an OR statement. Well, the way to do it that you would typically have with these is we'd want to use an OR. So let's go ahead and bring OR in. And let's create something called const is valid, right? So is valid is going to be OR array with length or large string. So now we can check is valid, and this will let a large string through. I forgot what repeat was. Does anyone know what repeat was? Oh, wait. What if I do I and then I do 30? Yeah, that'll work. So that'll come back true, but this comes back false, but this comes back false. Unless I have length, then that comes back true, right? So kind of the same things that we were doing before. Now, this is how we would typically do it. I wanted to kind of give an example of when we would want to actually use, or when implication can become helpful for us, so to speak. Okay. So because it is such a weak condition, it would be very easy for us, like we couldn't do this OR thing. We couldn't do any of that. But let's go ahead and let's move this to implies, and we'll move this to implies. Okay? So the issue with this I'm sorry. We'll keep that OR for now just so you could see. So this, of course, would be true. 1, 2. That, of course, would be true. But problem is, this is true. And say happy. That comes back true. Right? Because even though it was a string, it did jump in to check it. But because this one came back true, then it totally forgot about that. So we're going to need something a little stronger here, like with the and. So now that comes back as false. This comes back as true, but it also comes back as false. This right here, I hate when I do that. So now if I put in 23, that comes back as true because it never went in to do, we don't have any constraint or anything on there, right? So you might be wondering, well, why the heck would you even want to use this with and? So there's a lot of, so for instance, with the predicate data type or using some of the other monoids or things like that, or not really the monoids, but like equivalence and pred and things like that, they are centered around conjunction. So when I concat them together or do something, it uses an and. So doing this or like we had before, that rhymed. This isn't going to work with when we start getting into algebraic data types, at least with the ones that we have provided at our disposal right now. We're going to need to have something that works with conjunction. So let's go ahead and we'll change that back to and, but instead of doing that, let's change this to use all pass. I think it's all pass. Let's see here. Ramda docs. Is it all pass? Yep, it's all pass. So this is basically going to get conjunction on a list of things. So to get this to work with conjunction, what we want to do is use all pass. And we'll do some of this with a whole bunch of that. And do some of this, delete to the end, paste that, get rid of that. And I guess we'll bring this in. So how you would want this to work with conjunction, because that's basically what this is, we need to have another constraint. So our or, we're still going to need this or. And what we want to check is string, is array. And then we move like that. So now we see, because we're doing this all pass, and really it doesn't matter. The cool thing about this, oh, it does matter in some cases. Why did that matter? Oh, mattered because of this. So notice how we can just move this around and we still get the same answer, right? Isn't that neat? That's because of the and working with the and. Oops. But we really don't need to evaluate this at the head like we would if we were putting an and together before going on. It's nice because it can get us to bail early, but this allows us using and using implication to move things around, how would you say, like as we're building out how the predicate should be. So using this at the head of, one function or something like that might be a little over the top or things like that. But you would want to use something like this for validating or getting ready to validate, like, say, other business rules, right? This could be has a cookie, and then you go and evaluate the cookie in some way if the thing has a cookie. If it doesn't, then go ahead, right? Like you'll just do it with no permissions. But if the thing does have a cookie, then you want to go ahead and add that to it, maybe get the rolls off the JWT. And by the way, that's how I pronounce it. A lot of people say JWT, but JWT just sounds so silly and corporate. JWT, now that is something I can get behind. Sorry, I didn't mean to derail it there. That's what I do, though. I just derail things. So anyway, once we start, it may not be too clear like where this usage would come into play, because we haven't really talked about like the pred data type or equivalence or anything like that. But because this is so weak, we can mix it with such a strong condition such as and get a lot of power out of it. We also have a lot of reusability here that we wouldn't have before, because if we did make that an and, we would have to throw ors everywhere to combine all of these types of things if we use the and. So by using implies, it gives us a little more leeway to kind of make things a little more reusable, I guess, once you start building out a lot of these predicates. Because remember, these predicates are the key, like, to the applications. They're the things that define your business rules, the logic behind your app. All of that is based on these predicates. So even though it's kind of in the back of your mind a lot, you don't really have it in the foreground, you're going to have predicates all over your stuff, as if you have an app with any type of complexity, Yeah, that's pretty much all I have for now. Coming up on an hour, so we ended that, fairly on time. And most of this stuff about implies are just things I wanted to show. Number one, how to use another combinator other than and things like that. And as I find more uses for implication, I'm probably going to be adding implies to the library so you won't have to implement it yourself. But we'll have implies in actual crocs. So that way, when the cases do come up, it'll be available for you with a much better implementation, right? That's made for a library. But that's all I have. Are there any questions or anything before I get on to taking care of business for next up and whatnot? All right. Well, I'm going to get out of here. Next week, I will not be here. I have pager duty. Like I have the pager, so it would be kind of weird if I had to like leave something because the pager went off or something like that. So I have pager duty for work. I'm basically on call. So I'm skipping next week, but we'll be back the week after that. So yeah. Oh, yeah, and we will be starting on algebraic data types. Now that we got all this predicate stuff out of the way, we're going to start with, well, we'll start with the array, and we'll look at some different ways to view an array, like either as a product type or a sum type, or probably shouldn't be saying words like that right now. I don't want to lead to any confusion, but we're going to start taking a look at arrays. Yeah, so that's all I have. Again, it won't be next week. I meant next session. It won't be next week, but it'll be the following Tuesday after that. And I hope you guys have wonderful, or I'm sorry, I hope you people have wonderful days, or you folks. And it's been a pleasure. Talk to you later.